So we are now starting the topic on integrals. This is a topic you're not going to see until second semester of calculus. So we need to learn it now because we're going to start using it right away in AP Physics C. So the topics I'm going to cover are area under the curve, antiderivatives, and indefinite integrals. U substitution is a topic that is used in AP Physics C, but it's not going to be tested on the AP exam because it's harder calculus than they need you to express. And so I will be kind of focused on these topics. And when we get to U substitution, I'll talk about it, but we won't actually solve that integral. Okay, so what is an integral? It's the area under a curve. And you guys have seen area under a curve when we've talked about kinematics in your previous physics courses. So when you took the area under a curve of an acceleration graph, you were able to get velocity. And when you took the area under a curve of a velocity graph, you're able to get acceleration. Well, now we are going to start looking for area under a curve of a function that is not nice rectangles and triangles. And we don't have formulas to solve these very unique functions. And so that's where calculus comes in. So the equation for an integral looks like this or like this. It's got that kind of squiggly S symbol, and it has limits from A to B, which are the limits on your x-axis. And then the function f of x, and then it ends with dx. So the dx we saw when I talked about differentials, and this dx is not part of the function, but it lets you know what variable you're taking, what variable you are integrating with respect to. And I know I'm throwing a lot of big calculus words in there, but basically you're finding the area under a curve of the f of x function. So the expression you would read is an integral from a to b of f of x dx, but what dx really means is with respect to x. Okay, so one thing I wanted to highlight is the area under the curve. We're looking for the net area. And so this function stays on the positive side of the x-axis, but if it were to go in the negative side of the x-axis, the area under the x-axis is going to be a negative value, and you would have to subtract that from the positive area in order to get the net area, which you guys know from regular physics. Okay, so let's do this problem here. Given the fact that we are integrating from 0 to pi of sine x dx, and we know that equals 2, use your knowledge of the trig functions to evaluate the integral from 0 to 2 pi of sine of x dx. So we know what the sine function looks like, and we know what the area is when it goes from 0 to pi, which is half of a sine function. And then if we were to figure out what the net area would be for a full sine function, what would that be? So I'll give you a minute to think about it and then pause it if you need more time. All right, so the answer here would be 0. You've got an area which is given to you as positive 2 from 0 to pi, and then you know that sine is symmetric except on the opposite side, and so that would be negative 2, and the positive area and the negative area cancel out. Okay, so let's talk about antiderivatives. So an antiderivative is just an integral. I like this term better because anti is essentially the same term as the opposite. So it's basically the opposite of a derivative. If you're given the derivation of a function, the antiderivative would be the original function that the derivative came from. So let's use variables. If I use capital F to represent a function, then little f would be its derivative. If I were given little f as a function, so little f of x, I can integrate that function with respect to x and get the original function. So the dx coming at the end of a function little f of x was something that you saw when we talked about differentials, and the reason why that's there is for antiderivatives and integrals. So when you're taking an antiderivative, you have to first integrate, and we're going to go through the steps of that with a polynomial here. And then you have to plug in the limits. The limits always start from the upper limit minus the lower limit because you want the final minus the initial. So when we do this practice problem, because polynomials, we would take the exponent, multiply it out in front, and decrease it by 1, we're going to do the opposite. You're going to add 1 to the exponent, and it's actually written out in the equation sheet here. So you add 1 to the power, so this becomes 3, and then you divide by that new power, which then cancels out this 3 multiplier in front. 4 doesn't have a variable to it, but again, we can think of it as x to the 0. So we're going to add 1 to that 0 exponent and divide by 1, and that would give us 4x. So when you do a problem like this, you would think about what steps do you take to find the derivative and do the opposite of that. And again, as you're starting out with integrals, it's always good to have this equation sheet in handy so you can look at it. Okay, so this was the problem we were working on. Go ahead and see if you can take the derivative, which I kind of walked you through earlier, and then you have to do the subtraction of whatever that, or sorry, you're taking the integral, and then you have to take into consideration the limits. Once you get that integral function, plug in your upper limit and then solve, and then subtract it from your lower limit, solve, and then you will get the area under the curve. So take a second to do that. Pause the video if you need to, and I will reveal the answer now. It's going to be C34. This is your antiderivative or your integral equation. This is a symbol that they use after you've already integrated, and then you just draw a line after that function and show your upper and lower limit. Again, this is all new to you, so the more you practice, the more it'll become automatic. And then the next step is to take your upper limit, plug that in to the equation, and subtract it from the lower limit plugged into the equation and solve. Okay, so these are not equations that I'm going to solve with you. You can solve the first two, but what I do want to kind of emphasize to you guys is that not all of the functions are going to be integrated with respect to x, which is kind of our default variable. Most of the problems, especially in kinetics, are going to be integrated with respect to t or time. And then some of them are going to be random. In this scenario, we are integrating with respect to m, and so our function should have m in it. And it will get complicated because you will see functions with multiple variables inside the integral. And if, let's say, for example, I had x's and m's in this function, I would treat x as a constant. I would not treat it as a variable x because I am focused on taking the integral with respect to m as my variable. So all other variables that are not m are going to be treated as a constant. Okay, so when we took the derivative, we recognized that the constant values, for example, the number 1, the derivative of 1 would be 0. When we take the antiderivative, there is a possibility that there is a constant there, and we need to keep in mind the fact that there's a constant and we might not know what that constant is. When we do antiderivatives, that constant doesn't really matter. And you're going to see when we do this expression that the c constant ends up canceling out. So if I integrate my function with respect to x, I get my new function, which is the integral or the antiderivative function, big F or capital F of x. But I know that there could potentially be a constant in this function because when I take, again, the derivative of big F of x, that constant would cancel out to 0. Okay, the slide just changed because I had to fix this. When we solve this integral, we take our function and plug in our upper limit, so f of b plus our constant, and then we subtract it from our function with the lower limit plugged in, which is big F of a plus c. If you distribute this negative, you can see that this positive c will cancel out with this negative c, and we end up with the original f of b minus f of a without the constant in it. So anytime you do an antiderivative with limits, ignore the c altogether. And then I will talk about when we don't ignore the c. All right, so here we are integrating this function 6t squared plus t, and then the dt at the end lets us know that we're integrating with respect to the variable t. So we're going to look for t, and because it has a power or an exponent, we're going to use this from our equation sheet that tells us any variable to a power. To integrate, we need to add 1 to that power and divide by the new power. So you're going to turn this from t squared to t cubed and divide by 3. This you can think of as t to the first power, so you're going to add to that first power and then divide by your new power. I'm going to give you a minute to do that on your own. Pause the video. When you're ready to look at the answer, go ahead and press play. Okay, so the new function you should have gotten was 2t cubed plus 1/2 t squared. So if you didn't get that, then go back and make sure that you added 1 to your exponent and divided by that new exponent. And then we need to solve for the area under the curve, which means we plug in our upper limit and subtract it from the function when we plug in our lower limit. So here's our function with our upper limit 4 plugged in. We're going to subtract it from our lower limit -2. You have to make sure, especially if you have functions, that we distribute the negative sign, and then you end up with 150 as your answer.